Welcome, everybody. This is Chapter 1, Introduction to Fluid Mechanics. I've broken this chapter up into several videos just to reduce the amount of time in each video, so it's less time commitment, but also to maybe to stage the concepts a little bit more. Okay, so here's a quick overview of what we're going to talk about in this video. I'm going to give some basic definitions of what a fluid is, talk a little bit about temperature and pressure. That'll lead nicely into a discussion of what's called the Continuum Approximation. You've probably seen this in some of your other courses as well. And then we'll talk about something that's important, particularly for later in the course, something called dimensions, units, and the principle of dimensional homogeneity. Okay, so fluid mechanics, a definition here, is the study of fluids at rest and in motion. And if the fluids are at rest, it's called fluid statics. We're going to spend the first couple of chapters talking about fluids at rest. And fluids in motion is called fluid dynamics. And that's the chapter 3, 4, and 5. So let's start with what's the definition of a fluid? What's the technical definition of a fluid? And how does this differ from that of a solid? So you might have an intuitive sense for this, but here's the technical description. So imagine you take a solid here and it's attached, sitting on some surface here, not moving, and we apply a shear force, so a tangential force to the top surface. What'll happen with a solid is you'll get the surface will deform, but you'll get eventually the solid will resist that force and you'll get a static deflection. So that's the behavior that you're pretty familiar with of a solid. Now, in contrast, suppose you do the same thing with a fluid. So here I have a fluid sitting on a surface here, and on top I've placed a solid plate. Now, you could think of this as perhaps a thin sheet of wood, say floating on a pond or something like that. And now we apply a shear force, a tangential force to the top surface of this floating plate. What's going to happen in that case is the plate is going to move to the right. And the interesting thing about a fluid is the plate will have a constant velocity. Of course, it'll accelerate at first, but then it'll reach a constant velocity, and it'll have a velocity no matter how small the shear force is. So unlike a solid, a fluid cannot resist shear stress without deformation, without continuous deformation. And so a fluid will deform continuously for any applied shear force, no matter how small. So that's the technical definition of a fluid. There are two main classes of fluids, gases and liquids. So I've got a picture here of a glass. The glass actually contains two fluids, water and air. You might be surprised. So gases expand to fill their container, and their molecules are widely spaced at normal temperatures and pressures. At standard temperatures and pressures, the distance between air molecules is quite large. In contrast, fluids, if you pour them into a container, they retain their volume. They're what's called incompressible. Their density doesn't depend on pressure. We will get to that later on. And they form a free surface. So we have an interface between the liquid and the gas. And usually you'll see this. I'm going to represent it by this little triangle, that there's an interface. And in liquids, the molecules are much more closely spaced than in the gas. And that has some consequences. We'll talk about those consequences on the next slide. So before I go on to the next slide, I want to point out that you don't want to confuse the words fluid and liquid. Not all fluids are liquid. In fluid mechanics, anything that flows is a liquid. Anything that can't resist shear stress without continuous deformation. So air is in that category. Air is a fluid. Carbon dioxide gas would be a fluid. Water vapor would be a fluid. Okay, I mentioned that one of the characteristics of liquids is that their atoms are quite closely spaced together, and as a result, they often have strong cohesive forces. And you'll have noticed yourself that if you see a droplet of water, it tends to form into a sphere spontaneously. That's due to an effect called surface tension that we'll talk about later in the introductory chapter. Now, in water, surface tension is particularly high because, and I'm going to relate this, it's not critical for this course, but you may remember from your chemistry course that H2O is a polar molecule with the hydrogen being positive and the oxygen end of the atom being negative, and you get these electrostatic attractions between the hydrogen atoms and the oxygen atoms. So that's the source of the one of the main sources of the cohesive forces, and chemistry people call these hydrogen bonds. You don't need to know those details, but that is fundamentally the reason why water tends to bead up on surfaces and form a sphere. We'll come back to that concept later in the introductory chapter. Another key difference between liquids and gases is that liquids are about 1,000 times, 3 orders of magnitude, roughly speaking, more dense than gases at ambient conditions. So if you look at air near standard temperature and pressure, its density is about 1.2 kilograms per cubic meter, whereas the density of liquid water at room temperature is about 800 times that, about 1,000 kilograms per cubic meter. Now, just as a side, it always amazes me if you think in front of you right now, a meter by a meter by a meter, it's hard to imagine that there's a kilogram of mass in that volume, but there is. Okay, so let's just talk about this concept. We've just talked about how the definition of a fluid is that it cannot resist shear without continuous deformation. So if you have a situation like this fluid layer here is going to deform continuously. But now I'll ask you, can a fluid resist normal stress? So you've got the options. Yes, but only liquids. Yes, but only gases. Yes, both gases and liquids can resist normal stress. Or no, fluids in general, gases nor liquids, they can't resist fluid stress. Pause the video. Think about it for a minute. Okay, so the answer is that yes, both liquids and gases can resist normal stresses. And when I do this in lecture, I bring in this little piston arrangement. This is a piston and a column of air. And of course, if you push down with your hand on here, eventually the pressure builds up inside this little gap of air, and it eventually supports the weight of my hand. So you don't get continuous deformation. So even air in a cylinder can resist normal stresses without continuous deformation. And that normal stress here is actually, in a static fluid, is what we call pressure. Okay, I'm going to step back just for a minute. This is almost high school level material. I'm sure you've heard it before, but I want to make this connection because it kind of underpins everything in terms of fundamental understanding. So we know that if we add either heat through a Bunsen burner here to a substance, like adding heat to water, or if we put a paddle in here and we stir the water, that the temperature will increase. So let's remind ourselves what's fundamentally going on here. What is temperature? If the temperature goes up, what is that? Well, you should remember, I'm sure this isn't the first time you've heard this, that temperature is a measure of the kinetic energy of the atoms or molecules. I'm going to use a term here that I like. There's a famous American physicist called Richard Feynman. He refers to these as jiggling. So in solids, jiggle in place, as I've got a little GIF here that's doing that. The atoms are not free to move around. But if you heat it up, they'll jiggle in place more violently. Gases, on the other hand, are free to move around. They're not, they can expand to fill their container. And if you heat up this gas, the atoms or molecules in the gas will bounce around more vigorously. Of course, it's not just translational kinetic energy, it's vibrational and rotational. You may remember that from chemistry, but we'll call that just in general jiggles. So the jiggling becomes more energetic as the temperature increases, and that's really what temperature is. So I want to remind you that at the atomic or molecular scale, thermal energy is kinetic energy. It's just the vibrations and translations of the molecules and atoms. In thermodynamics, in Mech 309, you would have called that internal energy, giving it the symbol U. So at the atomic or a molecular scale, thermal energy is kinetic energy. I've got a little video here that shows something called Brownian motion. What you're seeing here is the jiggling of small grains of pollen in water. So evidence of this jiggling was first observed in 1827 by a botanist named Robert Brown, where he had a sample of water under a microscope that contained small grains of pollen. And you could see these pollen grains just bouncing around. And what you're seeing here is not the water molecules jiggling. What you're seeing is the water molecules on the different sides of the pollen grains bumping against the pollen grains unevenly and making them jiggle around. It was the first evidence of atoms and atomic motion and this concept of jiggling being internal energy. Okay, so let's put these concepts together. Fundamentally then, what is pressure? Okay, if I ask in the class, what is pressure? People will say force per unit area, but that provides really no physical insight into what's going on. So I want you to think a little deeper about what's the fundamental cause of pressure. So if you think about a gas here, and the atoms are vibrating because they have some thermal energy, what pressure is these atoms are bouncing against the wall and they rebound off. So the force of the atoms or molecules bouncing off the wall of the container is pressure. Now, of course, I've shown just a little GIF here with maybe 50 little molecules in it, but in reality, if you had like air, 28 grams of air would be 1 mole. That'd be 6 times 10 to the 23 atoms. So we're talking about a lot more atoms in a real container, but nevertheless, the same principle applies. That when these little atoms bounce off the surface, there's mass and a change in velocity. They change their velocity vector, and from Newton's second law, that produces a force, and that force is the pressure that's felt on the wall of the container. So that's fundamentally what pressure is. We're going to talk a lot about pressure in this course, and so I want you to keep sort of that concept in mind. Okay, so yeah, we can put some concepts together here. We just learned about thermal energy, and I'm sure you're not learning it from the first time. So now you can explain fundamentally, why does pressure increase if we heat the container? So let's suppose we put a Bunsen burner here and we heat this container. Then what's going to happen is the molecules, I can't do this in my animation, but these molecules are going to start vibrating and translating more aggressively with higher velocities. They're going to impact the wall with more kinetic energy, or change in momentum as they hit the wall. Will cause the pressure to go up. So yeah, you're going to get an increase in the velocity of the particles, an increase in the delta V as they hit the wall as temperature increases. And so that's the reason why when you heat a sealed container, the pressure in that container increases. One of the fundamental approximations in many of your courses, not just fluid mechanics, but solid mechanics as well, is called the Continuum Approximation. And this may not be the first time you've heard of this. So the Continuum Approximation, fluid properties are assumed to vary continuously. So we can assume we can have, for example, a point density that you can have density X, Y, Z, and that density varies smoothly throughout the domain of interest, or throughout the fluid. That's basically so that we can use differential calculus. However, we know if we look at an atom here, and I've got a bad diagram of an atom up here, we know that there's a very dense nucleus and some electrons and an electron cloud around the nucleus, and density does not vary continuously between the nucleus and the electron cloud. So we know that if we get down small enough, this assumption is not valid at the molecular or atomic scale. And so your book points out that when we make use of the continuum approximation, when we have a derivative of a property like density, we're actually representing the point property as an average over a small volume, small but large relative to the atomic scale. So your book says if you average over a volume typically of about 10 to the minus 9 cubic millimeters, you can assume a continuous variation of density. So this approximation is used widely in a lot of engineering courses. So your solid mechanics course too would apply this. You can't apply standard beam bending theory and beam deflection theory, for example, if you get down to the molecular scale. But it's an excellent approximation for most sort of macro scale engineering purposes, but it does break down at small length scales. So if you're doing nano engineering, you're getting out of the domain of the continuum approximation being valid. Okay, we're just sort of running through a bunch of concepts from chapter 1. I'm going to go through this fairly quickly. I'm sure you've seen it before to some degree in some of your other courses. Dimensions and units. Yeah, in fluid mechanics, we have something called 4 primary dimensions. So mass, m, length, L, T, denoted by capital T, and temperature denoted by a capital theta. And these little brace brackets means has dimensions of. So you would read this as mass has dimensions of m, length has dimensions of L, etc. So those are the primary dimensions. And then we attach a unit to each dimension. It's really just a way of attaching a number using an arbitrary measure. And I've shown a picture up here of the standard kilogram. This is the standard kilogram against, well, I don't think it's used anymore, but it used to be the kilogram against every other kilogram in the world was measured against. It was kept in the Bureau of Weights and Measures in Paris. It's the international standard kilogram. And so that's one way to attach a number to a mass, is just by an arbitrary standard. And of course, we're going to use the metric system international or international system, and we're also going to use the British gravitational system. And I'm sure you're familiar with the metric system. For dimensions of m, it's kilograms, meters, second, and Kelvin, and or degrees C if you want to convert Celsius to absolute units, you add 273. Keep in mind that the size of a Kelvin degree and the size of a Celsius degree are the same. So if you're talking about temperature differences, you don't add that 273. Now, here's the big thing. If you're working in the British gravitational system, the units of mass is slugs. It's not pounds. I'll talk more about this in a moment. Length is feet, time is seconds, and absolute temperature, we would use Rankine. And then there's the relationship between temperature in degrees Fahrenheit and Rankine. So what I want to say is that if you're given a weight of something on Earth in pounds, if you want to find out what its mass is in slugs, since weight equals mg, you want to divide by g. So you would take the weight in pounds and divide by 32.2 or 32.17 foot per second squared to get the mass in slugs. Okay, I'm going to say a little bit more about this because it is an area of some confusion. So the most important secondary dimension that we're going to deal with is force, F, and we use F equals ma, Newton's second law. That's really what defines the force. So force equals mass times acceleration. So m, and then acceleration is length per unit times squared. So ml t to the minus 2 is equivalent. Those are the dimensions of force. And of course, you know that a Newton is a kilogram meter per second squared. And so similarly, in the British gravitational system, 1 pound force is 1 slug foot per second squared. So be careful. Slug is the unit of mass, not pounds or pounds mass. And if you go to the conversion tables in the back of your book, you'll see that 1 slug is equal to 14.59 kilograms. So be careful of that. Always convert your weights into, if you want to get mass, you got to divide by G. You got to divide by 32.17 foot per second squared to get the mass in slugs. Here's a table of other secondary dimensions. They're pretty obvious, most of them. Area, it'd be length squared, volume length cubed. Of course, you can tell usually looking at the units. Velocity is meters per second, so that's going to be length per unit time for the dimensions. Most of them are obvious, but you do run into the kind of occasional non-obvious one, and I want to point this one out. Energy, heat, and work would have units of joules. A joule is a Newton meter. It's not immediately obvious that the dimensions are mass, length squared over time squared. So let's talk about that. So why does energy, variables that have units of energy, have this unusual dimension? Okay, so why does energy have the dimensions of m L squared time to the minus 2? Okay, here's a quick explanation. Joule is a Newton meter, and by F equals ma, a Newton is equivalent to a kilogram meter per second squared. So now we can take this and substitute it in here for the Newton. So now we have it all in terms of primary dimensions. So if we do that, we get kilogram meter per second squared, and we have this meter here, meter, and so kilogram meter squared per second squared. And so you can see from this that it has dimensions of mass, length squared over time squared. So if you get comfortable with that, you'll be able to figure out the dimensions of, well, the secondary dimensions of any variable you like. Now, this doesn't seem very important, but it will come back when we get to chapter 5 and we talk about dimensional analysis. So it's important that you practice a couple of these. It's very straightforward, but you should develop that skill. It's going to come back and we're going to need it. So energy, work, heat all have dimensions of mass, length squared over time squared. Another important principle is this idea of dimensional homogeneity. All the terms in any equation have to be homogeneous both in dimensions and units. So all the terms have to have the same dimensions and units. And I'm going to use an example here from Mech 309. If you haven't taken Mech 309 because you're a BME student, don't worry about it. It's called the first law of thermodynamics for a closed system. So I've got a control volume here. I'm looking at everything inside this box. We're adding heat. We're taking out work. And what the first law of thermodynamics says is the amount of heat that you add in joules minus the amount of work that you extract in joules, so these are all units of energy, equals the change in thermal energy, internal energy of the control volume. It either, the difference in what here either goes into thermal energy, it can go into kinetic energy, it can change the kinetic energy from state 1 to state 2, or it can raise something inside that control volume. It can gain gravitational potential energy, mg Z2 minus Z1. And all of these have the same dimensions and units. I just want to demonstrate that. Of course, we just showed that joules is kilogram over meter squared second squared. Work is also joules, kilogram meter squared second squared. Again, internal energy is energy, joules, kilogram meter squared second squared. But you look at these other terms, this is the kinetic energy now. We have kilogram, and this is meter per second squared. So it's going to become kilogram meter squared second squared. And here's gravitational potential energy, right? mg is the weight of whatever you're raising through some distance. So kilogram, g is meters per second squared, and there's the height in meters. So you get kilograms, meters squared per second squared. So you can see that each one of these terms has the same units and the same dimensions. When I am doing consulting work, I am very careful to always balance the units on my equations. If you accidentally miss a term or you don't square something, it's a super good way to pick up errors. And if you're doing something where you might get sued if you get it wrong, you really want to have all your wits about you and apply these careful techniques. So it's really useful to balance units and equations. I will be emphasizing that throughout the course, but also we're going to need it for chapter 5. We're going to need to be able to convert variables into their dimensions for chapter 5. Okay, and that completes this presentation. Bye for now.